stable for now, Paula. Further eruptions can't be ruled out.
Obviously, a lot of concern when the warnings first went out as well. Lucky it wasn't worse, but yes, I appreciate that update. And now to bring you more on our breaking news. Novak Djokovic has apparently arrived at the airport in Melbourne. He's a reminder that he is not a free man, and right now he's under a deportation order. You see him walking into the airport. It's almost 10 p.m. at night on Sunday night in Melbourne.
lot of cities across the east are on alert this morning. A powerful winter storm is bearing down. More than 80 million people are under winter weather alerts. We'll tell you when and where you can expect to see the effects. Sunday, January 16th. We are so grateful to have you. Thanks for waking up with us. Great to see you as always, Christine.
You too, Boris, especially after your double duty yesterday.
Yeah, I had to do an extra hour. No problem with that.
I know.
So we start with this dramatic hostage standoff in Texas, right? This morning, we're happy to report that all 4 hostages are safe after nearly 11 tense hours at a synagogue near Dallas.
Now, investigators say that suspect entered the congregation, Beth Israel Synagogue in Colleyville, Texas, during its Sabbath morning service and took the rabbi and 3 others hostage. Now, the services were being live streamed at the time. One hostage was released several hours into the standoff. After hours of negotiations, an FBI rescue team reached the synagogue and freeing the remaining hostages. And authorities say that lone suspect is dead. The suspect's been identified. Authorities are not revealing his identity, however, as this investigation continues. But of course, most likely will do so at some point.
Yeah, CNN security correspondent Josh Campbell now joins us live from Colleyville. And Josh, we don't know the suspect's name at this point, but sources tell CNN that officials are zeroing in on a possible motive, right?
That's right. The suspect is known to law enforcement. They're not releasing his name publicly, but so I say was because he is now dead. That after this elite FBI hostage rescue team stormed the synagogue behind me in an attempt to rescue those hostages. Now, this whole ordeal started earlier in the day. The synagogue was undergoing Sabbath services. There were congregants who could watch what was happening on a live stream as this man came into the building. He was ranting and raving. At one point, an FBI crisis investigator made contact with the suspect behind me. Those negotiations went on throughout the day. One of those 4 hostages was released, but it was around 9 p.m. last night that the
Hurry to Kohl's now for gear too great to pass up. Get Nike shoes, Adidas activewear for $45 and under, and
we're going to start this video off with a puzzle. For those who don't know, this is a numeric 8 puzzle. It scrambles the tiles and you have to move everything 1 tile at a time until you have always like 1 or 2 lines off, but I could not complete it because it would require me to go over the same line twice. I could not take my pencil off the paper and I could not go over the same line twice. This was just randomly brought up, by the way. My friend probably heard it from another friend, but no matter how many times I tried, I could not do it. I was always like 1 or 2 lines off, but I could not complete it because it would require me to go over the same line twice. I think I remember this because I tried so many times and it was bugging me. Neither of us knew whether it was impossible or we just couldn't find a way to do it. But years later, while learning graph theory, I read over this one theorem, then almost immediately took out a pencil and paper and drew the shape, which I still... If you did not get that, try this next one. If we have a bunch of nodes that represent locations, maybe cities, the correctly ordered configuration, can you logically prove whether it is or isn't? Now we'll get to the question of why would anyone need to know this, but for now just focus on the mathematical reasoning here. People who have just gone through high school math might be looking at this with no clue how to start. You might be waiting for a formula like you're being asked to solve for the volume of something. But that's not the case here. There's no formula, it's just logic and reasoning, and it's a different kind of math compared to what we see throughout high school. Again, we're trying to get the tiles in numerical order from left to right and going down, as if we were reading a book. So what we can do is lay the tiles out sideways, with the blank spot being at the end, and just look at them with a different perspective. But we're curious whether this is possible to solve when the last 2 numbers are switched. Now let's analyze what happens when we move a tile. If we do a sideways move on our game, it switches the location of the number and the blank spot. Notice that the relative order of the numbers does not change though. A sideways move actually preserves the order of the numbers. Then if we do a vertical move and bring the 5 down, it's now ahead of the 6 and the 8. In the linear model, the 5 moves 2 places backwards, bumping the 6 and 8 forward. In fact, whenever we move a tile up or down, it will move 2 places forward or backward respectively, and this is the only way to change the relative order of our numbers. Remember this, vertical moves can only move a piece 2 places forward or backward. Now let's go back to our initial setup real quick with a 7 and 8 out of order and look at how many pairs of numbers are out of order. The 1 and the 2 are in order, because 1 comes before 2 as it should. 1 and 3 are good, even 1 and 8 are good because 1 comes before 8 numerically as it does here. In fact, every pair of numbers is in relative order except 7 and 8. Thus we have 1 pair out of order. The goal is to have 0. So now let's do another vertical move and move the 6 down. On our linear number line, we know the 6 moves 2 places to the right. But before I move it, look closely. Originally, the 6 and the 8 are in order, because 6 is supposed to come before 8. Once I move it, they are out of order, and our out of order pairs changes from 1 to 2. But of course, we're moving it 2 spots. It was in order with the 7, but that changes as well, leaving us with 3 pairs out of order. So we did a vertical move, the number moved 2 places backward, which changed our out of order pairs by 2, 1 for each move. In fact, no matter what the order, every time a tile makes a single move along our number line, the out of order pairs will either increase by 1 or decrease by 1. If the 2 numbers are out of order, after a move they will be in order, thus however many out of order pairs we have will decrease by 1. And if they're initially in order, after the move they will be out of order, thus an increase in 1. Each single move makes the out of order pairs either increase or decrease by 1. But remember, when we move vertically, the only way to change the order of everything, tiles move 2 places over. That's our only option. If each move either increases or decreases the out of order pairs by 1, then after 2 moves you can either have a change of 2, a change of 0, however it may happen, or a decrease in 2. This is all that a vertical move can do. If our puzzle starts with 1 out of order pair, and these are the only options, no matter how many moves we do, adding to, subtracting to, or staying the same, there's no way to reach 0 out of order pairs, which was our goal. Thus, this puzzle is impossible. Hopefully this wasn't too confusing, but I really like this example. This is a famous problem in discrete math and is even taught at MIT in their Mathematics for Computer Science class. I like this example because there's virtually no mathematical background needed, but it did involve mathematical reasoning, and I'm sure most people just can't look at it and understand it immediately. Computer scientists and mathematicians have to do proofs like this all the time to understand a system or model from the ground up. And I hope you realize that it's very different than what you see in most high school math classes. This video is really on the mathematics that computer science and math majors see, as well as a few others. But I really wanted the focus to be on computer science because especially if you go into research, this is the kind of math you will need a foundation in. In this video and the next, I will show applications, but the proofs won't be anything that a mathematician would approve of due to time. Now let's go into another proof that's much easier and again needs no real mathematical background, just logical reasoning. Let's say you have an 8x8 checkerboard with the end corners missing. The question is, can you fill up every space with 31 domino pieces? Well, an 8x8 checkerboard has 64 squares. Minus 2 from the ends missing is 62. And 31 dominoes that cover 2 spaces each would cover a total of 62 spaces. But how can we show that it definitely is or is not possible to cover the entire board? See if you can get it, but the answer is fairly simple. Whether you orient the domino vertically or horizontally, it will cover 1 black space and 1 red space. Therefore, 31 dominoes would have to cover 31 red spaces and 31 black spaces. If you notice, those missing end pieces are both red, which means there are 32 black squares and 30 red squares. Like we said, we would have to have 31 of each, and since we don't, there is no way to cover the entire checkerboard with these, and our proof is done. These proofs are often the beginning of a discrete math class. You will learn proof techniques like proof by induction or contradiction that I won't go over, so no, it's not just all puzzles like these. While these were more general examples that might not have a direct, obvious application, you have to learn these proofs so you can then apply them to the more applicable problems, which I'm going to go into now, starting with graph theory. This is a huge field in math and computer science. In graph theory, graphs are not like x squared or sine of x. Graphs have a bunch of dots or nodes and lines that connect them or edges. The applications for this are endless. Maybe these nodes represent people and the edges are compatibility according to their dating profile. You might need to figure out an algorithm to best match everyone because lots of pairs of people will be compatible on these sites. Nodes could represent computers and the edges are cables that connect them, where data needs to travel the shortest path to reach its destination. Or nodes could represent destinations like cities, and edges are highways or roads that connect them. Many of these problems are not very easy, but here's a simple question you can use graph theory to solve. In a room of 27 people, can everyone shake hands with 9 others? Well, since this is graph theory, we'd have 27 nodes which represent the people. I won't show all 27 dots, but here are some to illustrate the solution. Now, if a pair of people shake hands, we can represent that with an edge. So right now, this person shook one person's hand, and so has this other person. The question is, can everyone shake hands with 9 others? To solve this, we only need one piece of background information. Look at this graph I just randomly found and count how many edges or lines leave this dot or node. Of course, there's only one. This is the degree of the node. Now what about node 4? Well, we see there are 4 edges leaving it, which is its degree. If we do this for every node, these are the amount of edges leaving each one, or the degrees. Add all these degrees up and we get 10. Now that we have that, count the amount of edges or lines that you see. You'll find there are 5, which is half the sum of the degrees. If we look closer, we'll see this is always true. Every edge connects 2 nodes. So that one edge makes both nodes have a degree of 1 for a total of 2. So we have something very important here. The sum of the degrees, adding every single line that leaves each dot, is always twice the amount of lines or edges that you see. Now we can go back to our problem. If everyone must shake hands with 9 others, then every node or dot needs 9 lines coming from it, meaning they gave 9 handshakes. Therefore, every node would have a degree of 9. If 27 nodes all have a degree of 9, then the sum of those degrees is 243. And we said the sum of the degrees is always twice the amount of edges. That means there are 121.5 edges, which is not possible. The amount of edges or lines has to be an integer like 1, 2, 103, etc. So the answer is no. In a room of 27 people, everyone cannot shake hands with exactly 9 others. If you did not get that, try this next one. If we have a bunch of nodes that represent locations, maybe cities, and edges which represent roads between them, can you find a path that travels every road exactly 1 time and ends exactly where you began? So you can pick where you start, and once you use a road, you can never use it again. I'll just tell you the answer is yes. You can go to each city and use every road only once. There is more than one way to trace this path out, but this is one way to go over every edge only once and end up exactly where you started. This type of path is called an Euler tour, where no lines are repeated and you end where you started. Now real quick, this is sort of a side tangent, and I don't know why I remember this, but when I was in high school one day, my friend challenged me in class to draw this shape, but with 2 conditions.
What if you could get rid of your kitchen garbage at the push of a button? Hey, I'm Matt from Pila, and I want to introduce you to my friend Lomi. At Pila, we're a team of engineers and material scientists, and we believe that waste can be designed out of your daily life. For the last 3 years, we've been creating something truly special, a solution to the world's garbage problem. Now, before I show you how Lomi is going to change the world, let's talk about why you're going to want one in your home. Maybe you live in a big city and have a green bin program. You know, those pesky little plastic bins with leaky bags under your sink that are amazing at producing that smelly, gross liquid sludge. Raccoons, anybody? Or maybe you don't have a green bin system where you live. Instead, you throw all your food waste into the garbage, which then goes to landfill, which produces methane, which causes climate change, all while still smelling pretty terrible. Lomi makes your life so much easier. Lomi can compost your food waste, that pesky packaging from your online shopping, even compostable plastics, all at the push of a button. You probably know us as the inventors of the world's first compostable phone case. You may have even seen our Lomi campaign on Indiegogo, where we sold more than 20,000 units, raised $7 million, and became the most successful crowdfunding campaign of 2021. Pila customers have eliminated more than 41.8 million plastic bags from the garbage in the last 4 years. Those 20,000 Lomis I was talking about, they're going to have even more benefit, preventing 1 million pounds of coal from being burned. We're just getting started. We want to get a Lomi in every home and prevent more than 1 billion pounds of waste from going to landfill. To create Lomi, we've spent more than 3 years completing 1,000 compost tests, probably more, and endless hours of product design and prototyping. Lomi isn't just beautifully designed. We've created something never seen before. an elegant home appliance that takes care of your garbage so you don't have to, giving you back time to do things you actually enjoy. Food waste creates 300 billion pounds of garbage in North America every year. Packaging in plastic, add that on top, which makes the number even higher.